are not here, but I'm truly thankful. Thank you to all the organizers. And again, I was feeling kind of territorial. You know, how come you're having a meeting of high level in Mexico? I'm not invited. So it's like I was very. No, it's like what's happening? But anyway, I got invited and everything was fine. To be honest, I don't properly work in numerical simulations, and that was probably why I was not invited to begin with. But I do have some very fertile collaborations with they're doing in terms of numerical simulations. In particular, what I'm going to tell you about today is in collaboration with Dominique Legendre and the two Benoits from Brussels, Universidad Libre de Bruselas. I don't know how you say it in French, but anyway, there you go. And of course, this work is in collaboration with two students, Gibran Raje from UNAM and Omar Atassi from both IMFT and the Free University of Brussels. And also, last subtitle is I just felt obliged to tell you about this particular talk because we're in Oaxaca, and Oaxaca has a lot to do with mezcal. And if you don't know what it is, I will tell you in 1 second. Also, I feel an obligation to give you some history lessons because, again, we're in Mexico, right? So we better know a little bit about it. And it gives me the opportunity to give you a wider context of why we're interested in this particular problem in two-phase fluid mechanics, right? So this is a picture of the origins of Mexico. This is the meeting of Cortés and Moctezuma. Moctezuma was the Aztec king in 1519 when Cortés arrived in what is now Mexico City, Tenochtitlan back then, and he was received like a king. You know, everybody was like, you know, cheering and said, "Wow, the god finally has arrived," right? And of course, you know, the two cultures were contrastingly different, and this, you know, image quickly became this, right? Where, you know, of course, the war started between the Aztecs and the Spanish conquistadores with the help of some local tribes, right? And again, this clash is resulted in what is Mexico today, right? It's neither European, it's nor pure Indian. So it's a very good mix of the two cultures, and that has a. Pardon me?
Very friendly mix.
Oh yeah. You know, well, you know, yeah, that has a lot of implications to what Mexico is, like modern Mexico is. And the first, of course, you know, it's love, of course, or I don't know if it was love or not, but you know, what is different between Mexico and other cultures and other places that have been conquered by imperialistic powers is the fact that actually the Spanish mixed with the locals, right? So, and this is during this period of time when actually they had a classification of the children, right? So if the mother was Indian and the father was European, then the children would be called mestizos, right? And so hence this word it means mixed, right? So most Mexicans, like myself, are neither European nor Indian. We're somewhere in between. And I found this article that measures the amount of DNA from different sources, and this is a random sample from people from Mexico City, right? I'm from Mexico City, so I'm somewhere in between where my DNA is probably somewhere over here, but you know, there's a wide distribution of genetic material. We're neither here, and there's a little bit of African, but basically it's a combination of Indians and Europeans. And this is everywhere in how Mexico works, in modern Mexico works. Again, this is a long introduction to multi-phase fluids, but I think it's important. One of the most important results of mestizaje is food, right? Because, you know, we had people from Europe that came with their, you know, their recipes, but, you know, they had no ingredients, no European ingredients. So they started cooking with whatever was around, right? And this is a delicious dish called chile relleno, which means stuffed pepper. And it, you know, peppers are from the Americas. Frying things in hot oil are from Europe. Dairy things are from Europe also. And this, I don't know where is it from. But anyway, it must be American, right? But anyway, so this is a very good example of how food became something which is mestizo, something is mixed, right? And, you know, Mexican food has been declared part of the universal culture by UNESCO. Anyway.
Fake news.
It is not fake news, believe me. One important, another example of mixing of cultures is mezcal. Mezcal is a distilled spirit that is obtained from the fermented juices of this plant, which is agave, and this type of drink is particularly important in Oaxaca, right? And again, it's a mixed, it's a result of mixing because distillation is a European invention, and the local plant is this one, right? Which you can find pretty much everywhere in Mexico and also in the southern parts of the United States. It's agave, right? So what you do is just basically take the core of it, cook it, squeeze it, or take the juices out, ferment it, and then distill it, and then you get this delicious thing which is called mezcal. Okay, what am I telling you all of this? This is the process how you make mezcal. You take out the cores of the agave, then you cook them, you get the liquid out, you ferment it, and then you go through 2 phases of distillation. Okay, just, you know, chemical engineering. What is most interesting about this process, and again is in sharp contrast to the subject of the conference, is not industrial, right? It's the exact opposite of industrial. Many of the processes to make mezcal nowadays are still done in small scale operations. Like this, you can, you know, if you have a chance to go visit a mezcaleria during your visit in Oaxaca, then you still see these processes that are conducted, you know, with donkeys and, you know, open pits and so on. And the distillation units are these very artisanal units. Again, why am I telling you all of this? With just one more thing, you know, of course, the result of distillation is mostly alcohol, which is here, is ethanol, and a whole bunch of other things, and this whole bunch of other things is what give this drink its magic, right? Its flavor. Right. Okay. So I was teaching this class in fluid mechanics. I was telling the students about the research projects, and then at the end of this lecture, one student from Oaxaca approached me and said, well, you know, I have a very interesting question for you. So it turns out that the traditional technique to measure, to determine if the mezcal is good, if the mezcal has enough alcohol, is to do this test, and you will see it here. And this is a maestro mezcalero from Oaxaca, and this is what they do. So it has basically a jet of fluid. It's poured into a cup, and if the amount of alcohol in the mezcal after the second distillation is good, you get this. You get bubbles, right? And the bubbles have a distinct long life. So they have to stand, the liquid has to be foamy for, I don't know, half a minute, something like that, which is very long compared to what you would expect for pure fluids. And this is the question that one of the students asked me. Said, see, why does it work? Why do they do it like that? Nobody knows, right? But this is how they do it, right? They still do it. Of course, it's cheaper just to go buy, you know, some density measurement device and just determine exactly what the proportion of alcohol is. but this is kind of cool, I think. Okay, so again, this is another a zoom of what I'm saying, and the people who make these tests call these pearls. Again, hence the name of my talk, pearls of mezcal. So why does this bubble have a particularly long life when the amount of alcohol is about 55% in volumetric fraction? Right? Of course, if we understand this, then okay, then we can extend this idea to other systems. You know, some fishes make bubble nests, you know, if you're doing some industrial stuff. And also it's very important for white cap measurement of wind speeds, right? If the bubbles are not sufficiently stable, then you would not get white caps, and then you could not determine the speed of the air from this visualization. Okay, so what we set out to do is a little bit of a recreational physics kind of project, but again, it involves a lot of physics, and of course, the key ingredient to understand this question is, to answer this question, is through numerical simulations, as I will show you in a little bit. So we do an experiment, and again, you know, once you tell students, you know, we're going to do some investigation with mezcal, actual mezcal, everybody's excited and everybody wants to join the project, right? So what we do is we go to the store, buy a whole bunch of different types of mezcales, right? And then we measure their properties, of course. We measure their alcohol content, and also we have some reference fluids. We have water ethanol mixtures. That's from France, right? That's not from Oaxaca, right? Actually, there's people who use something similar for whiskey and for bourbon, right? Similar thing, right? Anyway, all right, so I will show you different experiments. Again, it's fantastic to have your lab filled with your test fluids like this. And what we did is we reproduced the traditional technique. Instead of having this guy doing it, we have a pipette, and we empty the pipette into a closed container, and we just visualize using a high-speed camera. And this is, you know, a fairly well understood process where the collision of the fragments of the jet produce make the surface to break, and the breakage of the surface again produces these bubble clouds. And the bubble cloud just basically ascends here, and that's what produces the foam, right? And this is, again, a widely used process in many chemical engineering applications, and is fairly well understood, right? So again, what we want to do is we want to understand, first we want to answer if the method actually works. If it's just not, you know, it's just a hoax and we're just playing with it. And again, we do the experiment with water, pure water, pure ethanol, and then we take again our mezcal, right? And again, this is going to take a little longer here. Let me just go to the end over here, right? So for the same, given the same conditions, let me just, okay, I'm not tricking you. They lasted the same amount of time. And here you see the formation of this layer of foam. And here you don't see any foam, and here you don't see any foam, right? So that's a good, it's looking good. You see the pearls. There you go. We do a second experiment, again, trying to simplify the problem just to gain some fundamental understanding. So we inject bubbles continuously from below. Again, water, pure ethanol, and mezcal, right? And you just observe what is happening, and you see that the bubbles are rising from the capillary. They reach the top, they bounce, they do their thing, but eventually they break, they coalesce with the free surface, right? And same here, right? They stay here, they last a little bit, and then they coalesce. Here, maybe we can see this guy. There you go, right? In the case of mezcal, they're able to just hang out there for a little longer, right? And we want to understand why. Pearls. So these people who are making mezcal, they know something, right? So we go further a little bit, and we do a second, more controlled experiment in which we produce single bubbles. But to be able to visualize correctly, we do this little trick. We make the container to be completely full, a little bit above the rim of the container, such that the free surface has some curvature, and when you release the bubble, it will always rest in the top of the column, so that you can do a good measurement, a controlled visualization of the bubble on top of the fluid. Right? Here is the visualization. It's at 5,000 frames per second. It's sitting there for a little while, and it pierces. Let me just go back here. Right? You see the piercing does not occur at the top of the bubble, and it just retracts, right? And if you have seen this problem before, after the film pierces, then you have a concave surface, and then the fluid reacts, and you see a jet, which you will see better in the next one. This is a side view of the same bubble. It will pierce now. So the film retracts. And let me just speed it up a little bit. You see that the fluid reacts. You see the bubble. See, but this is the formation of this. It's being well studied, and it's interesting. But this is the summary of what you just saw, right? You see the bubble sitting on top. It pierces. The film retracts, and it leaves the cavity here, right? All right. So again, we do experiments with this particular mezcal that has the correct amount of alcohol, and we do, I don't know, maybe 100 experiments, many bubbles, to determine the residence time of this bubble at this. So it's about 30 seconds, which is a significant amount of time. There's a lot of variation also, but again, just one bubble, and it can sustain happy life on the surface for a long time. So what we do is then we adulterate the mezcal by adding either pure water or pure alcohol. And again, we just take the sample, add a little bit of alcohol, pure alcohol, and you see that the lifetime drops significantly. You have a sharp maximum of lifetime exactly at the correct amount of alcohol, right? So if the mezcal is not of good quality, it has lots of water or lots of alcohol, then the foaming would die immediately, as opposed to when you reach the correct amount, right? So the technique actually works. And then we go to, again, open all the bottles and do the test for all the types of mezcal, and it's same trend. A lot of variability, but we always see that the maximum is around that volumetric fraction of alcohol. Okay, but again, mezcal is ethanol water mostly, but it has a whole bunch of other things which make it more interesting but more complex. So we take one step back, forget about mezcal for 1 second, and we go to the lab and buy pure water, buy pure alcohol, and make mixtures of the two. And we do experiments in pure water, experiments in pure alcohol, and it turns out that if you have a mixture of water and alcohol without all the extra stuff, you see a similar behavior, but the lifetime of these bubbles is sadly shorter than that of mezcal, right? And if you have worked in this subject, you know where the conversation is going, but it's interesting, right? The fact that the mixtures of water and ethanol have this behavior is something is interesting to look at. It works too, okay? So we go back to the drawing board and say, what is the functional dependence of the life of a pearl? Well, it must depend on the physical properties of the fluid. This is the shortest list of variables that we can think of. And again, if we do the normalization of this function, we see that the dimensionless time normalized in this matter is only a function of Bond number. Again, only considering these 4 variables, right? And what is most important about writing this function like this is that the time must be linearly dependent with viscosity. Right? There's no other time variable here, so time and viscosity must always have the same power. So when we found this article. There's all these measurements of properties of water ethanol mixtures, and density goes linearly from the density of water to the density of alcohol. Surface tension goes from surface tension of water to surface tension of alcohol in a monotonic way, but viscosity does something strange. And this is because the nature of water, as we know, it's the most common liquid, but it's kind of bizarre. In the middle, it has a maximum value of viscosity because of the interaction of the two molecules, right? So, and it coincides with the place where the maximum lifetime of bubbles is, which is over here. This is our measurement with pure water alcohol mixtures, and this is just for comparison how the viscosity changes with volume fraction, right? So viscosity is playing an important part of the story, but it's not all, because again, this is just pure water alcohol, and it does not have all the other stuff that mezcal has. Again, this is about 2 seconds, and mezcal bubbles were in the order of 30 or so in lifetime. And also, there's another thing that we have not accounted for, and this is a visualization of a mezcal bubble, and it died. Here it's going, and you can see clearly what is happening here. There's convection, which is the result of something, right? And what is that something? We know what it is, but we want to understand what it comes from, right? It must come from gradients of surface tension. It's a Marangoni convection, but we need to pin down exactly what is the source of the gradients of surface tension. And this is where well, not yet. Another experiment that we did, again, once we visualize the fact that there is Marangoni convection, is that we took this mezcal, and added different amounts of a mixture of water and alcohol at 55%, such that this mezcal sample will be diluted, and now we get these measurements of lifetime, right? So it's mezcal, but then it has the right amount of alcohol-water proportion. So basically, the amount of other components is diluted once we add this, and then the lifetime just drops down, right? So it's not just viscosity, it's the amount of surfactants. And again, from our dimensionless analysis exercise, we plot the dimensionless lifetime as a function of bond number. And it turns out that we have this curve, which is very noisy, which is very frustrating. But we have the general trend like this, and we have an apparent maximum at around bond number equal 1. And now we get to numerical simulations, right? We can only answer so many questions through the experiments and through observations, but there's a lot happening in this film as the bubble film is draining during its lifetime, that we cannot answer experimentally. We would have to do a very complicated experiment, which would be nearly impossible to realize, right? So we use JADIM code because it was developed by people at IMFT. And I will not give you any details about this because we just had a lecture about this subject. And also, I'm not an expert in simulations of this sort. So if you have any questions, I will collect them and I will convey them to the experts. But the idea is exactly what we just heard from Stefan's talk, right? We have a Newtonian incompressible finite volume, and we account for surface tension. And what we do what they do is account for the transport of surfactants in the surface through this equation. Again, this is surfactants concentration in the interface, and this will lead to different values of surface tension as the surfactants are transported in the interface, and that will lead to Marangoni stresses that will drive the fluid within the film. Okay, so these are some tests of the performance of this numerical scheme. Again, if we have a bond number smaller than 1, then we have a nearly spherical bubble that sits mostly below the surface, right? Again, surface tension is strong. And if we have a bigger bubble where gravitational forces are bigger, then the bubble becomes deformed and it protrudes a little bit more against the free surface over here. One important observation of these numerical results, in addition to being in good agreement with experimental observations, is that the thickness of the film is not uniform, right? While in this case is nearly uniform, here the thinnest part of the film is not at the apex of the bubble, but is somewhere on the side, right? And again, this is an indication that there's a marginal regeneration phenomena occurring in these simulations, which is what has been observed in experiments, right? This plot shows the velocity of the fluid across the thickness of the film at a certain angle. It's actually an angle which is over here. If you measure the angle from the top to here, it's about near the thinnest region of the film. And again, we do comparison between two cases. Without surfactants, you see that the velocity is basically how the fluid is draining from the bubble to the free surface. So the bubble is draining always with a positive velocity. And what I mean to say is that the fluid is always going down along the thickness of the film. Okay? In the case where you have surfactants, again you begin draining like this, but then you begin to see that the velocity near the bubble can actually be in the opposite direction to that in the rest of the bubble. So the fluid is climbing up at some portions of the film, and if you have fluid going down near the center of the film and fluid going up near the top of the film, then you will have this regeneration of the film. It will not just drain, it will replenish itself with fluid, and hence it will live longer. So that's why we absolutely need numerical simulations, because we cannot determine this experimentally. Okay? It will be very hard at least. Huh? Okay? So here is a comparison between this pure water ethanol, the viscosity, and here are the numerical simulations. Okay? Sadly, we are only getting, at the moment, qualitative agreement, right? The time that it takes for the numerical simulation to predict the lifetime of the bubble is not up to scale. So it's not 2 seconds, it's about 1/10 that, right? So it would be somewhere over here, right? So we do see the maximum lifetime at the correct proportion of alcohol, but the magnitude of this time, the duration of this time is much shorter than that in the experiments. Here's again in dimensionless terms, our dimensionless time as a function of bond number. We have a maximum at around 1. And again, these are the numerical simulations. We see then an increasing trend for small bond numbers, a maximum, a peak around bond equal to 1. And then when the bubbles are larger, then the lifetime begins to decrease. Right? So there's, again, our key parameter is the bond number. But again, these simulations are off. This is order 10 to the 5, and if we just plot them in the same with their actual time, it's much below this. Right? I just put it there just for qualitative comparison, right? It's qualitative comparison, but it's good qualitative comparison, because what we want to know, we want to understand, is the physics, what is dominating this increase and then this decrease. Okay? Yes, I'm almost done. I will not tell you much about the comparison with theory, only two things, right? Of course, this problem has been studied by many people, right? In particular, Howell did a calculation for small bond numbers and found that the dimensionless time is an increasing function of bond number. And when you have large bubbles with surfactants, you have a decreasing function with bond number from these two papers. And this one in particular is very interesting because it does include the effect of marginal regeneration, and it predicts that the lifetime should decrease as you increase the bond number. Right? So these are only trend lines, and this explains why in this case the dynamics within the film are dominated by the balance between viscosity and surface tension, while in this case the dynamics of the film are balanced by the competition between viscosity and gravity. Okay? So we have a nice story that say that when you have both gravity and surface tension competing against viscosity, the bubbles should have a long, happy life. Okay? And with that, I hope that I was able to convey this idea of having to combine this recreational problem, no? Because it's very good for students. Students get really excited about this, especially in Mexico, because this is something of a national pride. No? We get to investigate this very fundamental problem in which we want to study the transport of surfactants in an interface, in a formable interface. We do experiments, but we absolutely need numerical simulations to gain a fundamental understanding about the physics. So with that, I thank you for your attention.